Hola a todos mis estudiantes. Nosotros tenemos 25 estudiantes por empezar. Empezar. I said empezar. Yo olvido el verbo empezar. Nosotros esperamos por los otros estudiantes. ¿Dónde son ellos? ¿Quién sabe? ¿Quién sabe? Okay, let's start. We have reached our number of students to begin. Okay, hello everyone, welcome. I had a Spanish 1 oral exam today, and it was funny because I'm taking the class like a student, like I'm full on having the students call me my first name, like I'm Ryan in that class. I don't even know if they know that I'm a teacher. I just look like a student who went through puberty really early. And so we had an oral exam today, and I wasn't going to do it, but I got put in a breakout room with another student, and I didn't want to let them down, so they have no partner for their oral exam. So I did the oral exam today. It was pretty funny. Okay, so let's just do a really quick recap for mi profesora es la maestra Viera. And I don't know why you didn't ask me that in Spanish. ¿Por qué no habla español? Okay. So we were learning about some different forces. We learned about the weight force, which is denoted by mg. So the weight force is the force due to gravity. It points downward. We learned about the normal force, which is denoted by F sub n. That's the force that keeps objects from moving through the floor. Okay. We learned about kinetic friction, which is mu sub k times the normal force. So that is the sliding friction. So if two surfaces are sliding past each other, then that is going to be kinetic friction. If two surfaces are touching but they're not sliding, then that's called static friction. So that's mu sub s. And there's a maximum value that static friction can take, which is mu sub s times normal. Okay, so this is called static friction. Okay, and then lastly, we have the elastic force, which is kx. Okay. So what are we going to learn about today? Today we are going to learn about diagonal forces. So for example, let's suppose that we have a force that is at an angle, and let's say that the angle is 30 degrees, okay, and it's a force of size 80 newtons, okay. It turns out that diagonal forces, are equivalent to a vertical and a horizontal force. Okay? So this diagonal force is completely equivalent to an up force and a rightward force. Okay? So a diagonal force is like two forces combined, one being vertical and one being horizontal. So how do we figure out what are the sizes of these two forces? Okay. Well, what you do is you use trigonometry on this force triangle here. So the vertical force is going to be the vertical leg of this right triangle. So because this right triangle is opposite the angle, it's going to be sine, so 80 sine of 30 degrees. Okay. And so that is going to be 40 newtons. So I could say that this upward force is 40 newtons. And then this horizontal component is going to be 80 cosine of 30. 80 cosine of 30 is about 69 newtons. So what that means is that an 80 newton diagonal force at an angle of 30 degrees is equivalent to an upward force of 40 newtons and a side-to-side force of 69 newtons. Okay? So that's what you want to do with diagonal forces. You always take a diagonal force and you turn it into a vertical force and a horizontal force. Okay? Is everyone clear on that? I hope so. Now let's talk about Newton's second law. In 2 dimensions. So what if we have 2 dimensions? We have diagonal forces have vertical forces and horizontal forces. Okay, so it turns out that Newton's second law, net force equals ma, is equivalent. Newton's second law works in the vertical direction and in the horizontal direction. So the net force equals ma, there's a net force in the x direction, which equals m times the x acceleration, or the horizontal acceleration. And then the net force in the y direction is m times the y acceleration. So what do I mean by the net force in the x direction? Well, the net force in the x direction is going to be the left forces minus the right forces. And the net force in the y direction is going to be the up forces minus the down forces. Okay? So what if I had an object and it has, I'm representing the object as a dot, and it has 2 upward forces and a downward force, and then 2 leftward forces and a rightward force. So I'm going to give these numerical values. So maybe this is 100 newtons, this is 50 newtons, this is 75 newtons, this is 200 newtons, this is 30 newtons, and this is 70 newtons. Okay? So if this is a picture of the forces that are acting on the object, then we would say that the net force in the x direction is the left forces minus the right forces. So the net force in the x direction is 100 minus 50 minus 25. Okay? Or 75, my bad. That should be 75. So that's 100 minus 125. So that means that the net force in the x direction is negative 25 newtons. So that means the object would move to the left, would accelerate to the left. The net force in the y direction is up forces minus down forces. So I have 70 and 30 going up. And then I have 200 going down. So I have minus 100 newtons. Is the net force in the y direction. So this is going to accelerate downward and to the left. So the object is going to accelerate downward and to the left. All right? So Newton's, so to summarize what I'm trying to say here, Newton's second law applies both vertically and horizontally. And to get the net force in the x direction, you do left forces minus right forces. To get the net force in the y direction, you do up forces minus down forces. Okay? Boom. So this is what you need to know. These two things are these two spaces here are the things you need to know for today's lesson. So the rest of the class is just going to be examples. Okay? I'm going to do 3 examples for us today. So the first example I want to do is you have a box and it is on a floor. So here's a box on a floor. It has a mass of 4 kilograms. Okay. And it is being pulled by 2 forces. One of these forces is 20 newtons at an angle of 25 degrees. And the other one is 10 newtons at an angle of 60 degrees. Okay? So what I'm going to do first is I'm going to draw what is called a free body diagram. And a free body diagram is simply we represent the object as a dot, and we draw arrows coming out of the dot that represents each force, okay? So representing the object as a dot, we have 20 newtons at 25 degrees, okay? We have 10 newtons at 60 degrees. We have a weight force, which is going downwards. So these two are applied forces, so I put them in explicitly. Okay. And so the weight force going down is 4 times 10. That would be mg equals 40 newtons. And then the upward force is the force from the floor, which is the normal force. Okay? Now what I'm going to do is I'm going to take these diagonal forces and I'm going to break them up into components. So I'm going to write them as a vertical force and a horizontal force. So 20 sine of 25, and this would be 20 cosine of 25. For this force, we're going to have 10 sine of 60 and 10 cosine of 60. Okay? So what I'm going to do is I'm going to actually redraw the free body diagram with those diagonal forces rewritten as a vertical force and a horizontal force. Okay? So let's start out with the 20 Newton one. 20 sine of 25 is 8.5 newtons. Cosine of 25 is 18.1 newtons. So this, okay, so this 20 Newton diagonal force is equivalent to 8.5 newtons up and 18.1 newtons to the side. Okay? This 10 Newton force, 10 sine of 60 is 8.7 newtons. And 10 cosine of 60 is 5. Notice how this force goes up and to the left. So this 10 cosine of 60 is actually going to be to the left with size 5 newtons. Okay. And then I also have the additional forces. So I have the weight force of 40 newtons, and I have the normal force. Okay? So, now what we're going to do is we're going to write expressions for the net force in the x direction, and we're going to write expression for the net force in the y direction. Okay? So, based on this diagram, it tells us what the net force is. And based on this diagram, it tells us what the net force in the y direction is. The net force in the y direction is going to have a variable. So go ahead and type into the chat what you think the net force, write an expression in the chat for the net force in the x direction, and write an expression in the chat for the net force in the y direction. Okay? I'm going to wait for you guys. Ustedes escriben en la chat. Okay, so we have one response for the net force in the x direction. That's good. If someone else could maybe type in the y direction. So the y direction is actually going to have 4 terms because there are 4 forces in the y direction, and one of them is going to be a variable. Okay? So the net force in the x direction is going to be 18.1 minus 5 equals 13.1 newtons. And the net force in the x direction is equal to m, which is 4, times the acceleration in the x direction. Okay? So 13.1 divided by 4 is 3.3 meters per second squared. So the acceleration in the x direction is 3.3 meters per second squared. So as a result of these forces, what, you were right! Put it back in the chat. Someone retracted a message and it was correct. Anyways, this box is going to accelerate to the right at 3.3 meters per second squared. So now to get the net force in the y direction, we do the up forces minus the down forces. So we have the up forces are normal force, 8.7 newtons, 8.5 newtons, and the downward force is 40 newtons. Okay? Very good. And that actually is going to equal m times the acceleration in the y direction. Now it turns out that the acceleration in the y direction is 0. Okay? So why is the acceleration in the y direction 0? It's because in order to accelerate in the y direction, the box would have to be lifted off the surface. Okay? But you need to apply at least 40 newtons upward to lift the box off the surface. Okay? We only have about 17 newtons of upward force being applied. 17 newtons is not greater than 40 newtons. So the box is basically stuck to the floor. And because it's stuck to the floor, it can only move side to side. It can't go up into the air or through the floor. Okay? So the net force in the y direction is going to be 0. So that tells us that that the normal force is 22.8 newtons. Okay? There you have it. So we know the acceleration of the box and we know the normal force. All right, let's do another example. This example is, let's suppose you're on a playground. Okay. So we have a 20 kilogram child on a playground. Okay. And the child refuses to leave the playground. So the parent has to come in and drag the child across the playground. Okay? I don't know, maybe this has happened to you before. I can remember when I was a kid, there used to be this place called Discovery Zone, which I think is out of business now. It was kind of like Chuck E. Cheese's, which I think Chuck E. Cheese's is also out of business. But Discovery Zone was like the McDonald's play area, but like 10 times as large. So basically, what you would do is you would pay to go into Discovery Zone for the day, and you could just go into this giant play area, and it was all self-contained, and yeah, and so it's called Discovery Zone, and then the parents would just, I don't know, sit outside of the play area and drink beer, or I don't know, eat pizza or something like that. And when it was time to go, um, when it was time to go, my dad or my mom would be like, "Okay, time to come in," and I would always refuse. So I would go deeper into the tubes. I was basically like a rat inside the tube, and then eventually the employee had to come in and drag me out. Okay. So this is that kind of scenario. So let's suppose that the coefficient of kinetic friction between the child and the playground floor is 0.4. Okay. And let's assume that the parent is dragging the child with 300 newtons at an angle of 30 degrees above the horizontal. Okay? So what I'm going to do is I'm going to represent this as a free body diagram. Okay, so I'm representing the child as a dot. And then I'm looking at the forces that are acting on the child. So there's the 300 Newton diagonal force. Okay. There is the normal force from the floor. Because the child is being dragged to the right, friction is going to point to the left. So we have kinetic friction pointing to the left. And then we have the weight force going downward, which is mg equals 200 newtons. Okay? So the first objective after we've done the free body diagram is we want to take any diagonal forces and we want to write them as a vertical force and a horizontal force. Okay? So the vertical component is going to be 300 sine of 30, which is 150 newtons. The horizontal force is going to be 300 cosine of 30, which is 260 newtons. Okay, so now we redraw the free body diagram. So we now have two upward forces. We have the normal force, and we have 150 newtons. And then we have a downward force of 200 newtons. Then the rightward force is 260 newtons. And the leftward force is friction, kinetic friction, because the child is slagging across the playground floor. Okay? So let's go ahead and start off with Newton's second law in the y direction. Okay? Who can type into the chat an expression for the net force in the y direction? Very good. Excellent. It looks like someone typed in down forces minus up forces. Oh my gosh, we have a former student who typed down forces minus up forces. Welcome, Fu. Thanks for dropping by. So up forces minus down forces would be normal plus 150 minus 200. Okay? So the net force in the y direction is normal force minus 50, and that has to equal 0. Okay? So why is that? Well, because the upward force is only 150 newtons. That's not enough to lift the child off the ground. You could imagine a situation where the parent drags with so much force diagonally that it actually lifts the child up off the ground. Kind of doing something like this. Like if I pull diagonally hard enough, I actually can lift it off the ground. Like that. Okay? But 150 newtons is not enough to lift the child off the ground because the child has a weight of 200 newtons. So that tells us that the normal force is 50 newtons. Okay? Now, here's an important point. Once we know the normal force, we can now calculate friction. Friction depends on the normal force. Okay? So now I can calculate friction. Kinetic friction is mu sub k times normal. The coefficient of kinetic friction is going to be a given. It's 0.4. And the normal force is 50. So that means that kinetic friction is 20 newtons. So now I can fill in the actual values of some of these forces. So this is 50, and this is 20. All right. So now once we know friction, we can now write out Newton's second law in the x direction. So who can tell me an expression for the net force in the x direction? Actually, who could just tell me what the net force in the x direction is? There's a good question in the chat while I'm waiting for an answer, which is what would happen if the upward force was greater than 200 newtons? In that case, the child would lift off the surface, and because the child is no longer in contact with the surface, you would have no normal force, and you would also have no friction because those are both contact forces. So the child would just accelerate through the air. So yeah, if the child lost contact with the surface, we would only have weight force and the applied force would be the only two. Okay. Excellent. So people have typed into the chat correctly that the net force is 240 newtons. So that comes from 260 to the right minus 20 to the left. 240 newtons. And that equals m, which is 20, times a sub x. So notice how you can have an acceleration. It's just a horizontal acceleration, not a vertical acceleration. So that's why the net force in the y direction was 0, but in the x direction it's not equal to 0. So that says that 12 meters per second squared is the acceleration of the child in the x direction. Okay? We're going to do one more example. And that example is a skier. Consider a skier of mass m on a frictionless slope of angle, let's say 55 degrees. Okay? Now, so here's the slope. It looks kind of like this. And we want to know what is the acceleration of the skier down the slope. So here's the slope. It makes an angle of 55 degrees. Here is the skier. Okay. So this is a little bit tricky because the acceleration is diagonal. We have an x acceleration and a y acceleration. So that is tricky. So here's what we're going to do. So here's what we are going to do. We are going to rotate the piece of paper so that now the skier is accelerating horizontally. So this is the x direction, okay? But before we do that, let's draw a free body diagram, okay? The normal force points perpendicular to the incline, okay? So perpendicular to the incline would be that way. So that is the direction of the normal force. If you're on an incline, the normal force points diagonally. The weight force points directly downward. And so that is going to be m times g, which is 10. So 10m is the weight force, okay? So now I'm going to rotate my piece of paper. And I'm rotating it by 55 degrees. Like that, okay? So notice how I rotated this arrow right here, 55 degrees. Look at it. It goes, boop. I rotated it 55 degrees so that this normal force should point up and down. So what that means is that this angle right here is 55 degrees, okay? So that means that, okay? So that means that the vertical component of this force is going to be 10 times m times cosine of 55 degrees. And the horizontal component of the force is 10 times m times sine of 55 degrees. Okay? So now I'm going to redraw the free body diagram. Okay? 10 times cosine of 55 is 5.7. So if I redraw my free body diagram, I have normal force going up. I have this component of the weight force is going down, and it's 5.7 m. So again, I just said that the skier has a mass m. I did not specify the mass of the skier. And then the leftward component of the weight force is going to be 10 times sine of 55 times m. So that's 8.2 m. Okay? Now let's look at, and there's no friction because it's a frictionless slope. Now let's do the net force in the x direction. Who can type in an expression? It's very simple. What is the net force in the x direction? Who can do it? Because there's only one force. I'm waiting for a response. Net force in the x direction. 8.2 m. Yes, it's actually going to the left, so it's negative 8.2 m. Don't forget that m equals m a sub x. Now you can see here that mass is on both sides of the equation, so the mass cancels out. So what that means is that no matter the mass of the skier, every skier would have the same acceleration down this slope, regardless of what the mass of the skier is. So that's why I said a skier of mass m, and I didn't give you a specific mass, okay? So those canceled out, and I get that the acceleration is negative 8.2 meters per second squared. Okay? So that's a little bit tricky. If you have a slope, what you want to do is you want to rotate the piece of paper so that the slope is now flat. But in doing so, you take gravity and you rotate it to an angle. All right, so that's a little bit. We're going to spend more time on that in the next lesson. So if that doesn't make sense to you, don't worry, we're going to get some more examples. Okay, so those are my 3 examples. I want to just summarize what are the steps. So let's just do a summary of what are the steps of solving this problem, this type of problem. So the first step is to draw a free body diagram. Okay? So this would be the free body diagram. This would be the free body diagram. This would be the free body diagram. Okay? Okay? Then, once you draw the free body diagram, you want to use trigonometry to write the diagonal forces as vertical and horizontal. Okay, so we do that. And then once we do that, we redraw the free body diagram. And when we redraw the free body diagram, all of the forces are vertical or horizontal. So for example, right here, I redrew the free body diagram where there are no more diagonal forces. Okay, for this one, I redrew the free body diagram so there are no more diagonal forces. For this one, I redrew the free body diagram so that there are no more diagonal forces. Okay? Then what you do is you go to Newton's second law. So you have net force in the x direction is m times a sub x. Net force in the y direction is m times a sub y. Okay? The net force in the x direction is left forces minus right forces. The net force in the y direction is up forces minus down forces. And then the last step is you solve the equations. And you want to be careful because you might have that the y component of the acceleration is 0. You might have that the y component of the x acceleration is 0, as we'll see in the next lesson. Okay? So that is my lesson for today. So we are going to go to the Zoom room at this time. Nosotros vamos a the Zoom room. I don't know how to say room in Spanish. Okay.